In a moment, we are going to see how we can use data to update our initial beliefs about the unknowns in our model, primarily about the model parameters. We are going to use what's called Bayes' rule or Bayes' theorem to arrive at the posterior distribution. Before we can do that, we need to briefly discuss the concepts of data generating process and likelihood function. These two concepts are critical for understanding how we can connect data with the model and the model parameters. Well, the data generating process is a model that describes how our data could have been generated. It is a chain of hypothetical events that led to each and every observation in our dataset being observed. This chain of events can include both deterministic steps and random steps. Deterministic steps are the steps that, for each combination of inputs, return a unique value for the output. Random steps are the steps that, for each combination of inputs, return a distribution of possible values of the output. Data generating process can include the unknowns, the parameters. Typically, when we have unknowns, when we have parameters in a DGP, we seek to use data to assess what the values of these parameters are in order for us to be able to draw predictions, to be able to characterize the effect of variable, and to be able to extract other quantities, compute other quantities of interest from using our model. Now, likelihood function is in a way a summary of the data generating process. The likelihood function is a function of model parameters, and it is specific to the DGP and to the data that we have on hand. The likelihood function is typically computed as the probability that the data that we actually observe could have been generated using our model with the specific values, with the given values of the model parameters. To see the DGP and the likelihood function at work, we are going to take a look at an example, and we are going to look at the logistic regression. The logistic regression, Logit, is a model that is used to connect independent variables with the binary outcome variables. A binary outcome variable is a variable that takes the values of 0 or 1. One way to think about the data generating process behind the logistic regression is to think of it as consisting of two steps, one deterministic step and one random step, one stochastic step. At the first step, the values of the independent variables specific to each observation in our data, together with the values of the coefficients, determine the value of theta for each observation that we have in the data set. To mimic this process, we could take the vector of the values of the independent variables for each observation, multiply them by the vector of coefficients, and apply the inverse Logit function. At the random step, at the stochastic step, nature draws the actual observed values of the dependent variable from Bernoulli distributions with the probability parameters equal to the thetas. The values of the independent variables and the value of the dependent variable are known and observed. The betas, the coefficients, as well as the parameters of the Bernoulli distribution used to draw the values of the dependent variable, are not observed. They are unknowns. So let's try constructing a likelihood function using this information. In addition to this description of the data generating process, we are going to need a hypothetical data set. So here at the left side of the slide, you can see hypothetical data set with two independent variables, one dependent variable, and 3 observations. The variable x1 takes the values of 1, 2, and 0. The variable x2, the second independent variable, takes the values of -1, 1, and 3. And the variable, the dependent variable, has the values 1, 0, and 1. Let's follow through this data generating process until we arrive at the probability that we could in fact observe the observed value of the dependent variable in each of the cases, in each of the rows of our data set. At the first step, we can compute theta for each row that we have in our data set. To do that, we are going to need to take the values of the independent variables and multiply them by the parameters beta 1 and beta 2. We are also going to add intercept beta 0 to this sum. Once we do that, we can apply the inverse Logit function, and this will give us the formula for theta I for each row in our data set. As we know from the descriptions of the data generating process, nature draws the actual observed values of the dependent variable from Bernoulli distributions with the probability parameters equal to those thetas. Therefore, the probability that we could observe the value of 1 as our value of the dependent variable is going to be equal to this theta. And for each observation, the probability that nature would return the value of 0 as the value of our dependent variable is equal to 1 minus theta. And so if we actually observe the value of 0, then the probability of observing the actual observed value of the dependent variable is going to be equal to theta I if we actually observed 1, and is going to be equal to 1 minus theta I if we observe the value of 0. The likelihood function is constructed as the probability that we could observe the dataset that we actually observed given the values of the parameters. And so because we drew our observations independently, that likelihood function is going to be equal to the product of the probabilities of observing the value of the dependent variable in each observation given the values of the independent variables and beta, taken separately for each row. Once we combine this information, we can arrive at the expression that you can see in the last row on this slide. And this is, as you can see, the likelihood function. It is a function of betas and only of betas. So what can we do with this function? Well, if we were to use the maximum likelihood estimation approach, we would try finding betas such that they maximize this likelihood function. In the Bayesian context, we are going to use the likelihood function in a different way. As discussed earlier, in the workflow of Bayesian analysis, we are going to start by treating each parameter as a random variable. We are going to figure out which values they can take and assign a distribution, a probability distribution, to each of those parameters. That's going to be the prior distribution. Then, according to the biases rule, the posterior distribution is just a combination of the likelihood and the prior according to this formula.